This talk is about infinity and infinities. But what is infinity, and how do we define an infinite set? What are countable and uncountable sets? Are some infinities larger than others? And can we do arithmetic with them? And what is the continuum hypothesis? Which set is larger? The set of counting numbers, 1, 2, 3, 4, etc., or their squares, 1, 4, 9, 16, etc. Because every square is included among the counting numbers, the squares clearly form a smaller set. But the table below shows that there's an exact matching between the two sets, so they must have the same size. Such paradoxes greatly troubled the 17th century astronomer Galileo Galilei. And in his book on Discourses and Mathematical Demonstrations Concerning Two New Sciences, Salviati, representing Galileo, mentioned them. He was also disturbed by the fact that a longer line clearly contains more points than a shorter one, and yet they can again be matched up exactly, as pictured below. Such situations don't occur with finite sets, but it was more than 2 centuries before infinite sets were understood. In 1831, the German mathematician Carl Gauss protested that the use of an infinite quantity was never allowed in mathematics. 20 years later, Bernard Bolzano of Prague began to clarify the nature of infinity in connection with Galileo's paradoxes. But the great breakthrough came in 1888, when the German algebraist Richard Dedekind proposed that a set is infinite when it is similar to, that is, it can be matched exactly with, a proper part of itself. Otherwise, it is finite. This definition gradually came to be accepted by the mathematical community, causing the British philosopher Bertrand Russell to declare that solving the difficulties which once surrounded the mathematical infinite is probably the greatest achievement of which our age has to boast. Much of the credit for exploring the infinite came with the German mathematician Georg Cantor in the 1870s. Now sometimes called the man who tamed infinity, Cantor defined a set to be countable if we can count it. That is, if it can be matched with the counting numbers 1, 2, 3, 4, etc., so that we can write its elements as a list. We've already seen that the squares are countable. Simply match 4 with 2, 9 with 3, 16 with 4, and so on. But many larger sets are also countable. For example, the set of all whole numbers, positive, negative, and 0, can be matched with the counting numbers as shown here. And we can say, for example, that 2 is the 4th number, that -3 is the 7th number, and that every whole number appears somewhere in this list. An even larger countable set is the set of all halves as listed below, starting with 0, then a half and minus a half, 1 and minus 1, etc. So that we can say, for example, that 2½ is the 10th number and that every half appears somewhere in the list. In a similar way, we can list all the thirds, such as 5 2/3, and the quarters, such as -9 3/4. And so these sets are also countable. How about the rational numbers, that is, the fractions? Do they form a countable set? At first this may seem unlikely, not least because between any two rational numbers there are infinitely many others. But as Cantor proved, the set of all rational numbers is countable, so that they can all be written in a list. The picture here indicates how all the positive rationals can be counted. Here, the top row has the counting numbers. The second row has the positive halves, the third row has the positive thirds, and so on. We then trace the curved line shown here, ignoring repeats such as 1 and a half, and we get the list below: 1, then 2, 1/2, 1/3, 3, 4, 1.5, and so on. Every rational number is included. For example, 2/3 is number 8 in the list. So the set of positive rationals is countable. We can then list all the rational numbers by alternating positive and negative ones, as we did before. But not all sets are countable. For example, as Cantor proved, the set of all real numbers is uncountable. We cannot write them all as a list. We'll prove this for the set of numbers between 0 and 1, because if this is uncountable, then so are all the real numbers. So assume for contradiction that the set of all numbers between 0 and 1 is countable. We can then list them all with the first number as 0.A1, A2, A3, A4, etc. in decimal form, and similarly for all the following numbers. We repeat, this list contains every number between 0 and 1. We next choose numbers x1, x2, x3, x4, etc. between 1 and 9 in such a way that x1 differs from A1, x2 differs from B2, x3 differs from C3, and so on. Then the new number 0.x1, x2, x3, x4, etc. differs from the first number in the list in the first decimal place, differs from the second number in the list in the second decimal place, differs from the third number in the third decimal place, and so on. It therefore differs from every number in the list, which was supposed to contain all numbers between 0 and 1. This contradiction shows that our original assumption was wrong, and that the set of all real numbers is indeed uncountable. We note also that because the rationals are countable and the real numbers are uncountable, some infinities are larger than others. Indeed, to take this further, we can show that there are infinitely many infinities, all of different sizes. Another question which Cantor asked was, can one match all the points in a line with all the points in a plane? Adding that the answer seems to be clearly no. But it's yes, as he eventually showed by taking the line to be the interval of all points from 0 to 1 and the plane to be the unit square with coordinates from 0 to 1. In one direction, he then matched each point of the square with coordinates 0.A1, A2, A3, etc., 0.B1, B2, B3, etc., with the point 0.A1, B1, A2, B2, A3, B3, etc. on the line. And in the other direction, he matched each point 0.x1, x2, x3, x4, x5, x6, etc. on the line to the point of the square with coordinates 0.x1, x3, x5, etc., 0.x2, x4, x6, etc. As Cantor himself commented, I see it, but I don't believe it. In 1924, the German mathematician David Hilbert illustrated these ideas by considering the arrival of guests at a hotel. Clearly, if you arrive at a hotel with a finite number of rooms which are already occupied, then you cannot be accommodated. Instead, we'll assume that the hotel has a countable number of rooms which are already occupied. If you now arrive at the hotel requiring a room, how can it accommodate you? To do so, the hotel manager moves the guest in room 1 to room 2, moves the guest in room 2 to room 3, and in general moves the guest in room n to room n+1. Everyone else is then still accommodated, while room 1 is now free and you can stay there. Suppose next that 10 people turn up, each requiring a room. In this case, the manager can move the guest in room 1 to room 11, the guest in room 2 to room 12, and in general, the guest in room n to room n plus 10 for each number n. Rooms 1 to 10 are now free, and the new arrivals can all stay there. In this way, the hotel can accommodate any finite number of arrivals, such as 1,000 or 1,000,000 new guests. But suppose now that a countable number of people turn up. In this case, the manager moves the guest in room 1 to room 2, the guest in room 2 to room 4, the guest in room 3 to room 6, and in general, the guest in room n to room 2n for each number n. The odd-numbered rooms are now all free, and the new arrivals can all stay there. Using this idea, we can develop an arithmetic of infinities. To do so, Cantor introduced the cardinality of a set. For finite sets, this is just the number of elements. For example, the set 2, 3, 5, 7 has cardinality 4. For any countable set, such as the set of all integers or all rational numbers, he proposed the symbol ℵ₀, where Aleph is the first letter of the Hebrew alphabet, with larger infinite sets having cardinalities ℵ1, ℵ2, etc. in increasing order of size. The cardinality of the set of real numbers is usually denoted by the letter C, standing for the word continuum. And so, because the rational numbers are countable and the real numbers are uncountable, ℵ₀ is less than C. Returning to Hilbert's hotel with a countable number of rooms, we can now write some infinite equations. The number of guests before any others arrived was ℵ₀. The successful placing of 1 or 10 new guests then gives us the equations ℵ₀ plus 1 equals ℵ₀, and ℵ₀ plus 10 equals ℵ₀. And similarly, we have ℵ₀ plus n equals ℵ₀ for any finite number n of new guests. The successful placing of a countable number of guests then shows that ℵ₀ plus ℵ₀ equals ℵ₀. And we also have c plus n equals c for any finite number n, and ℵ₀ plus c equals c, and so on. A question posed by Hilbert and others then arises. We know that the cardinality of the integers or rationals is ℵ₀, and that the cardinality of the real numbers is c, where ℵ₀ is less than c. Is there an infinite set with cardinality lying strictly between these two? Cantor and Hilbert both believed the answer is no. But can this so-called continuum hypothesis be proved? Before we try to answer this, let's look at a logical paradox due to Bertrand Russell. This paradox turned set theory upside down in the early 20th century. In a certain village, the barber shaves all those who don't shave themselves, but obviously doesn't shave those who do shave themselves. So who shaves the barber? If the barber shaves himself, we have a contradiction, because he doesn't shave those who shave themselves. But if the barber doesn't shave himself, there's a contradiction, because he shaves those who don't shave themselves. So the question can have no answer. Such logical paradoxes led the mathematical community to seek more rigorous forms of set theory. The most widely accepted of these was proposed by Ernst Zermelo of Germany and Abraham Frankel of Israel. Around this time, Hilbert and others were seeking a set of axioms that would underlie the whole of mathematics. These axioms would need to be consistent so that contradictions could not appear, and would also have to be complete so that all mathematical results could be proved from them. But in the early 1930s, their hopes were suddenly dashed when the Austrian logician Kurt Gödel proved his so-called incompleteness theorem, that in any axiom system where one can add and multiply, there are true results that cannot be proved. And there are statements which are undecidable in that they cannot be proved either true or false. Returning to the continuum hypothesis about whether there's an infinite set whose cardinality lies between L0 and C, Gödel showed that this cannot be disproved within Zermelo-Fraenkel set theory. Then in 1963, the American mathematician Paul Cohen astounded the mathematical world by showing that this cannot be proved within Zermelo-Fraenkel set theory. Combining these two results, we see that the continuum hypothesis cannot be proved either true or false. It is undecidable. This is the last of this series of equations and their origins. In these 18 presentations, I've tried to describe what these equations are and where they've come from. If you'd like further details on any of them, you can find them in my book, Some Stories, Equations and Their Origins, published by Oxford University Press. There's a link in the text below.